So today we are going to start our discussion of the frequency response to transistor amplifiers. And all right, found a mouse because I want to pull up an LT spice simulation that I created in a moment. Go ahead and have that kind of going in the background. Okay, so to this point, we have kind of made an assumption that the voltage gain of a transistor amplifier is constant regardless of frequency, and that is very much an erroneous assumption. Okay. In reality, the capacitors that we use to bias our circuit, so those are our coupling and bypass capacitors, exhibit some influence on the low frequency characteristics of our amplifier's voltage gain. And the internal capacitances that we talked about when we developed our high frequency model on Monday influence our amplifier's high frequency gain. So typically, if we incorporate the effects of all of these capacitances together, we are going to have a frequency response that's going to look something like this. So on this axis will be our voltage gain in decibels. And then on this axis will be frequency expressed either as linear frequency or as angular frequency. Doesn't particularly matter, it's going to look roughly the same. And what we should have is a response of basically this form. And I'm going to make some annotations on this little drawing right here, but I believe I mentioned it previously. We should see something that looks bandpass filtery, and that is exactly what this thing is. So I am going to put some markings on this little picture. So I'm going to say that the difference between this dashed blue line and the red line is going to be 3 decibels, because we typically measure our cutoff of a filter as 3 decibels below the maximum value, right? That's when our signal is only at half of its power. So at our low frequency cutoff, we're going to call this F low or omega low. And over here on the other side, we're going to have F high or omega high. So everything to the left of our low frequency cutoff is what we're going to consider to be our low frequency band. Everything to the right of our high frequency cutoff is what we're going to consider our high frequency band. And everything in the middle is what we are going to consider the mid band. Okay. So all of the analysis that we've done to this point has effectively been mid-band analysis, where our gain is effectively constant or independent of frequency. So we can break this frequency response up into effectively a transfer function, since things are dependent on frequency. And so our voltage gain transfer function, AV as a function of omega, could be written as our mid-band gain, which I'm going to call simply A mid. And then we're going to have polynomials that are going to represent our zeros if they're in the numerator and our poles if they're in the denominator, right? So we might have S plus omega Z1. Actually, let me do omega ZL1 for low frequency 0, all the way out to S plus omega ZL sub n. So just n poles, depends on how the circuit is constructed and all of that kind of stuff. There's going to be n zeros in the low frequency response. Then we might have S plus omega Z H1 all the way out to S plus omega ZH. I'm going to call this P. And this will be all divided by S plus omega P L1 out to S plus omega PL, let's call it M. And then S plus omega ZH1, omega PH, sorry. All the way out to S plus omega PHQ. So what I'm trying to illustrate from this, these indices, so N, P, M, and Q, are just me trying to say that there may be a different number of poles in the low frequency response than the number of poles in the high frequency response, than the number of zeros in the low frequency response, than the number of zeros in the high frequency response. So we may have 3 zeros here, 5 zeros here, 8 poles here, 4 poles here, or something like that. It won't actually work out that way. They're usually going to be an even number. But anyway. So we could actually split things up into a specific low frequency response and a specific high frequency response, because the capacitors that we use for coupling and bypass are usually significantly larger than the internal capacitances of our transistor. So we could effectively split this thing into an AV low as a function of omega. That is our mid-band gain times S plus omega ZL1 all the way out to S plus omega ZLN over S plus omega PL1 out to S plus omega PLM, and an AV high of omega that is effectively represented in the same way. We'll have our mid-band gain times the poles and zeros of the high frequency transfer function. So S plus omega ZH1 out to S plus omega Z HP over S plus omega PH1 out to S plus omega PHQ. Now let's talk about what's happening, okay, in our system that causes our voltage gain as a function of frequency to behave this way. So in our low frequency band, effectively what's happening is we are observing the effects of those coupling and bypass capacitors impedance changing from looking like an open circuit at very low frequencies to a short circuit at midband frequencies. Because these capacitors are so much larger than our internal capacitances, all of our internal capacitances are still going to look like open circuits for the entirety of our low frequency response. So effectively, that allows us to analyze a circuit where we're just assuming that all of those internal capacitances are open circuits or just do not exist. So we just look at the circuit with the coupling and bypass capacitors and pretend the high frequency capacitors are not there at all. When we're going to look at our high frequency response, now we're looking at our high frequency capacitors transitioning from behaving like open circuits to behaving like short circuits, where all of our low frequency capacitances are already behaving like short circuits, okay? So we're well past the frequency where their impedance is effectively negligible. So that's how we're going to split things up. We're going to look at a low frequency response and then a high frequency response. And from those two things, we can construct the entire frequency response of our circuit. So we're going to start with a common emitter amplifier. I'm going to make some assumptions here. I'm going to be honest, some of them are just to make the math easier because I got tired of doing the algebra. But I tried to back up every assumption that I'm making with a little MathCAD sheet that shows you effectively how much error is being introduced at particular frequencies when I make that, so that we can see whether or not the assumptions that I'm making really have any impact on what's going on and what frequencies they're most messing with things. I also created, let me go to the right folder here.
This was for lab.
Was it? Well, son of a bitch, because I was supposed to do this before your lab. I also designed a simple BJT-based amplifier. I think you guys probably use MOSFETs, maybe not. A BJT-based amplifier where my goal really was just to have a gain of greater than 100, and I think I got it in somewhere in the ballpark of 150-ish. So if we simulate this thing over a ridiculously large frequency band, and let me get my keyboard out here. So I'm going to add a trace, and I want the voltage at the output divided by the voltage at my input, because that's gain, as a function of frequency. And we get this curve. Let me change the color of that to make things a little bit better. So down here for this particular configuration, we can see that we're decaying when we're going effectively from right to left at about negative 40 decibels per decade. So there's got to be 2 zeros going on over here that are making that kind of happen. We flatten out right here. We'll talk about that in a moment. And then we transition up, and now we're hitting our midband. So this bit right here is the midband, and then whenever our midband gain drops by 3 decibels is when our low frequency response starts, and whenever our midband gain drops by 3 decibels on this side is where our high frequency response starts. So I want to ask you guys a quick question here, and the shape of this depends very much on the capacitors that I chose to use. Why do you think there are 2 plateaus here? Why doesn't it look like this one? So that first plateau effectively represents the gain of the amplifier when this capacitor CE isn't a short circuit yet. So that's the gain of our system with emitter degeneration. And then as this smallest capacitor gradually turns into a short circuit, we see that our gain increases to our midband gain, which would just be the gain of this part right here.
If we
So-
decide that one down there about like.
So let's see what happens if I make this one 10 micro. It moved things over a little bit. If I make it 100 micro, and if I make it larger and larger and larger, it's just going to smooth that out to give me effectively the exact style of response that I wanted to look at, or that I would expect to see. And then, so one thing that I really like about LT Spice and its various models for things, so if we hit this thing, if we look at this particular transistor, the 2N3904, so this is a transistor that you guys could buy from Amazon, Mauser, DigiKey, and all of that kind of stuff. The model is very, very involved. So it tells us what the reverse bias saturation current is, 1 times 10 to the negative 14 amps. So that would be what, 10 femtoamps. It tells us that our early effect voltage is 100. Beta is 300, and then it has a whole bunch of other things that I honestly don't know what they mean. Then we get into the junction capacitance for the base collector junction is built in. The junction capacitance for the base emitter junction is built in, which is why we see our high frequency response on the other side without actually having to put any capacitors in there. So LT Spice actually does a really, really good job of modeling these systems. All of the stuff is already kind of built in. So what we're going to do today is just try to figure out using circuit analysis why it does this. Yes. The phase angle. So let's talk about that really quickly, actually. We can see when we're in the mid band that our phase angle is 180 degrees. Why is that? This should be a no-brainer question. Because the gain of a common emitter amplifier is negative, blah, blah, blah. 100% right. Yep. So at very, very low frequencies, we don't invert our signal, which should make sense because there's this big capacitor right here that's effectively blocking everything from happening. So almost no input voltage is actually going to get applied because the impedance there looks very, very large compared to these two resistors in parallel and the internal impedance of our capacitor. But as this capacitor starts to look more and more like a short circuit, our phase gradually gets pulled down until we get here where we're fully in the midband. Yes.
Yes, stupid question. But if you know like how it behaves in that mid frequency, can you guess what the corner frequencies would be with a low and high?
So can you guess what they are? Not particularly. What we are going to do today, so I guess it depends on what you mean by guess. So what we're going to do today is we're going to analyze the circuit and figure out where our poles and zeros lie with some approximations. And then on Monday's class meeting, I'm going to introduce the concept of I think it'll be the open circuit time constant method, which is literally just, it's making an assumption that you have what's called a dominant pole, and that your frequency cutoff will be around that dominant pole. So it's just a different method saying we don't really care what's going on at low frequencies. We just want to know what our bandwidth is, kind of thing. So it's a good approximation, but it does make an assumption that you have to have a dominant pole to use it, and that's not always true. So what we're doing today will still have uses whenever we don't have dominant poles. And for what it's worth, there's also a method of estimating where the high frequency response begins, which is, I believe, using if the low frequency response is the open circuit time constant method, then the high frequency response is the short circuit time constant method. Effectively, all that entails is associating a pole and a zero with every capacitance in the system. based on what resistance is connected there, but we'll get to that in a little bit. All right, so the circuit that we are interested in today is our low frequency response of a common emitter amplifier. Yes. I do not, thank you. Low frequency response. That was about to get real awkward because I was definitely going to run out of room. Thank you for that, Nathaniel. So before we get into this here, I want to give you guys, I guess, I hesitate to call it a warning, but it is a little bit of a warning. And what I mean by that very specifically is every other time I've taught this class, I didn't do BJT amplifiers literally at all. When I covered the frequency response of transistor amplifiers, I did nothing but MOSFETs where channel length modulation was ignored because it made the math easy. I'm telling you this because if you decide to go watch my old videos, they will be practically useless. So I'm going to harass my student worker to make sure that these videos get updated quickly and uploaded quickly and regularly, so that if you have any questions about anything and need to refer back to the videos, you will actually have the information that you're expected to be able to synthesize. Okay. All right, so our circuit of interest is the arguably simple common emitter amplifier with a full biasing network. So here's our resistor R1. Here's our resistor R2. Here's our resistance RE in parallel with some capacitance CE. Here is our resistance RC. And then I'm going to put or capacitively couple a load resistor to my collector node. And I'm going to capacitively couple an input signal with an assumption of some signal resistance RSig onto my base node, like so. So what I'm going to do in this analysis is I'm going to split this up into 3 distinct stages. So I'm using these dashed lines to separate my stages. Like so. So the stage to the left is what I'm going to call my input stage. And I'm going to define a new voltage here. I'm going to call the voltage directly at the base of the transistor Vx. And I'm going to call the voltage here directly at the collector of the transistor Vy, so that I could develop a transfer function for the input stage of the amplifier that would be Vx as a function of omega divided by Vn. In the middle here, I have my actual amplifier stage, which will have a transfer function of Vy over Vx. And then over here to the right, I have my output stage, which has a transfer function, if I had labeled my output voltage anyway, of V out over Vy, such that overall, my voltage gain as a function of frequency is just going to be Vx over Vn times Vy over Vx times V out over Vy. So this is very similar to how we approach things when we were just worried about the mid-band response of our amplifiers. We're just extending this technique effectively to looking at our frequency response. So we're going to analyze the most important stage first, which would be the amplifier stage. So before we jump in there, we need to discuss what we are going to consider to be the mid-band gain of our amplifier, because we want to be able to pull that part out and then have our poles and zeros multiplied by that thing. So what should the mid-band gain of this amplifier be? It's just a simple common emitter amplifier. In the mid-band, we are assuming that the resistor Re is shorted out by the capacitor Ce. So we're not neglecting early effects, so it'll be negative GM R naught in parallel with RC. Okay. So A mid will be negative GM R naught in parallel with RC. And then we'll see what all shakes out from that. Okay. So put a line here. And let's look at our amplifier stage kind of in a vacuum. Okay. So here I would have my, did I call it VCC or I call it VDD? It doesn't matter. Just used to MOSFETs. Sorry about that. So there I have my VCC. And I'm going to draw this as a resistor, but I'm going to call this some impedance ZC, which just represents the impedance connected between my collector node and my small signal ground. Here's my voltage Vx. Here's my voltage Vy. And then here's my impedance ZE, representing whatever impedance I see connected between the emitter node and ground. So let's figure out what ZC and ZE are going to be. Okay. So we'll do ZE first because I feel like it's much easier, although ZC isn't particularly difficult. So if we look back at our original diagram here, what do we see connected between the emitter and ground? A resistor in parallel with a capacitor. We're going to deal with impedances and we're going to be working in the S domain so that we don't have J's and Omegas all over the damn place. Okay. So I think that we would see RE in parallel with 1 over SCE. Everybody okay with that? So we'll do a tiny bit of math here. So to me, this is going to look like RE divided by SCE over RE plus 1 over SCE. And if I multiply through by SCE over SCE, I wind up getting RE divided by 1 plus S RE CE. I'm expressing my impedance in this particular form because hopefully it's pretty obvious that like, oh, it looks like there might be a pole associated with this thing because I have a 1 plus S times something there in the numerator. So that's how I'm going to wind up expressing all of my impedances so that it's easy for me to pick out poles and zeros, at least some of the time before the algebra gets too gross. So what's the impedance connected to our collector node? So I hear some discussion among you guys, so that's good. I think some of you just said it was RC. That's part of it, right? There's also the capacitor in series with resistor RL is also connected between the collector and ground. So we can't forget that part too. So we're going to see those two paths in parallel. So that's going to look like RC in parallel with 1 over SC out plus RL. Make sure I labeled that as C out. I did. Okay. And then we'll algebraically manipulate this guy as well. So that's going to look like RC times 1 over SC out plus RL divided by RC plus RL plus 1 over SC out, multiplying through by SC out over SC out gives me RC times 1 plus S RLC out over 1 plus S RC plus RL times C out. We okay with that? Okay. So let's treat those two impedances right now like they were just resistors. What would this look like? What kind of amplifier would this be? Obviously a common source amplifier, but we have something connected between the emitter and ground, so it's seeing some sort of degeneration. So I gave you guys a terrifyingly gross equation in 335. I want to check something here really quickly. One of my student workers should do this. I want to see if they did it. So what I have been working on when you guys are nice enough to leave me the hell alone, which is not often enough in my book, but that's okay, is rewriting notes for some of those 335 relationships to try to get things in smaller, less horrifying forms. And so with any luck, Lindsay will have uploaded the thing that I'm looking for. This looks like it. So got some notes here, common emitter amplifier with a current source, biasing things, easy peasy. Common emitter amplifier with degeneration with a current source, biasing it, again, whatever. And then down here, we have a common emitter amplifier with emitter degeneration. Okay. So not expecting you guys to be able to follow along with all of this algebra. I'm just going to skim through it, just going to show you the results. But if you want to see how it was derived in a less terrifying form, it's available for you guys on Moodle. Okay. So scrolling down here to our voltage gain, I know this still looks real gross, but it's way less gross than what you have currently in your notes if you want to go back and look. It is a horrifying thing here, and it's a mildly unsettling thing here. So we have this relationship right here where we have RC times RE minus beta R naught over this mess of things. Okay, so that's where we're going to start from with our transfer function for how this stage is going to work. Okay. So I'm starting with the relationship that Vy over Vx is equal to RC times RE minus GM R pi, that's just beta, R naught all over R pi RE times 1 plus GM R naught plus R naught plus RC times R pi plus RE. And now we're going to introduce, yes, Hannah, how may I help you? So if we didn't include that, we would have problems, right? So we wouldn't be getting as accurate as a response. So effectively, we are including the loading effects of that capacitor in series with that resistor on the amplifier's gain, because we know even in like when we short circuit that capacitance C out, our voltage gain for this system with every other thing else being as it is would be negative GM R naught in parallel with RC in parallel with RL. So that little bit there, that capacitor in series with that resistor will have an impact on the voltage gain. So we're including. We could not include it and it would make things a little bit easier, but it's not going to be as accurate as it could be. And I'm already introducing enough error to try to get away from some of the horrifyingly gross math. Anyway.
So are we, like, is the V outlet and output stage between CO and RL?
Mhm.
We, like, account for damage whenever we evaluate the output stage?
Exactly right. So it's going to look like a voltage divider at the output stage, and for what it's worth, it's also going to look like a voltage divider at the input stage, which is exactly what we saw when we were looking at these in 335 with all of those capacitances represented by short circuits. We're treating it the same way, breaking it down into discrete stages that are, they're going to be gross because we're dealing with frequency response, but they're going to be less gross than if we just try to do everything together at once.
On the same thing.
Mhm.
How does this relate to PMD?
So that's what we're about to do. We're about to take this thing and put it in terms of A mid. So I'm going to introduce the first simplification here. Okay, so I brought up a MathCAD sheet here. Let me scroll up to the part that we're on. So I put in literally our circuit's parameters. Okay. This is the voltage gain that I just gave you guys. And what I'm going to do is I'm literally going to throw that RC times RE away, under the assumption that it's going to be smaller than whatever it is that we're dealing with. So I want you to notice here that when I throw that part away, I wind up introducing 0.003% error. So a very small amount of error just by throwing that away for this particular configuration of resistances, capacitances, and transistor parameters. And at the very, very end of this worksheet, I actually have what our voltage gain would be with everything tied together, without making any of those simplifications versus what our voltage gain is with these simplifications, and it's within 1%. But anyway, getting ahead of ourselves. Well, it's within 1% for the frequencies of interest. It's almost 10% at very, very low frequencies. And I'll explain why that is in a moment. So I'm arguing here that I can throw away that RC times RE from the front here without messing with things too much. And it looks like the math bears that out. There is no frequency dependence on anything that I'm looking at right here. So this is just strictly looking in terms of the resistances and all that kind of jazz, and we're getting 0.003% error. Okay. I feel like that is relatively acceptable. It's about as good as we're going to get. So we're going to say that this is approximately negative GM R pi R naught times RC over R pi RE times 1 plus GM R naught plus R naught plus RC times R pi plus RE. We're going to wind up replacing these REs and RCs with ZRs and, or excuse me, ZEs and ZCs here in a moment. I'm just keeping the math light and breezy for as long as I can. Okay. So we expect our midband gain for this to be negative GM times R naught in parallel with RC. Well, R naught in parallel with RC is R naught times RC over R naught plus RC. I already have an R naught times RC in my numerator. So now I need to figure out how to get an R naught plus RC out of my denominator to be able to pull my midband gain out of this thing, okay? And it's not particularly difficult to do because I can see that I already have an R naught plus RC term right here. So if I multiply and divide this bit right here by R naught plus RC, I get to pull that midband gain right out in just 1 to 2 steps of algebra. So let's do that formally. So we would have negative GM R naught RC times R pi times R naught plus RC times R pi RE 1 plus GM R naught divided by R naught plus RC plus R pi plus RE. And from here, I can call this negative GM R naught in parallel with RC times. So I'm going to skip one small step here. I don't like that R pi in the numerator, so I'm just going to divide the denominator through by a factor of R pi to get rid of it. Okay. So that I will have 1 over RE times 1 plus GM R naught divided by R naught plus RC plus RE over pi plus 1. Oh, excuse me, yes, R pi, thank you. That's just. So are we okay with the algebra thus far? Trying to take things as least gross as possible. Okay. All right, so we're at a point now where we've got our mid-band gain taken out of this thing, okay? We're gonna wind up messing around with this part over here on the left because we know that this RC is really now a ZC that we have to deal with. So how can we extract that out from that? And then we're gonna mess around with this part on the right. We're gonna start with messing around on the part on the right. And now I'm gonna introduce my second bit of error here. And this is purely because I ran out of time to do the necessary math, okay? So I'm just being upfront about it, okay? So what I'm looking at here is I'm scrolling down. So I've set up my worksheet such that I can change the frequency of operation and therefore the value of S. So I've got my ZE put in, I've got my ZC put in, and then effectively I'm leaving this negative GM R naught in parallel with ZC in place in both cases because the math isn't that horrifying for that part. And then the only thing that I'm changing between here and here, and actually I need to fix that. I just realized that says ZE when it should be ZC, so the error might not be as bad as I thought it was. Or it might be worse. Let's find out. Better, awesome. Great. So that's at this particular frequency. Oh, should I have taken that off? We can play around. Let's look at things here. So let's look at low frequencies. 1 hertz, the difference is 1.5%. At 100 hertz, or yeah, 4%. At, I don't know, let's jump up to 100 kilohertz, it's less than 0.5%. So realistically, this isn't introducing all that much error by me leaving RC here as opposed to putting ZC in. And the only reason that I'm leaving RC as opposed to ZC is because I've got effectively polynomials inside polynomials, and it just requires a bunch of algebra, and I did not physically have the space to do all of that at my house at 2 o'clock this morning. So that's the first real quote unquote large amount of error that we're going to introduce. Here now, how may I help you first? So I have the Z's defined here. Oh, actually, so we are going to play around. So there's a couple of, let me put it this way. There's a couple of steps missing from right here to right here that we are about to go over. But what I'm trying to show you here by showing you the MathCAD sheet is that leaving just RC here instead of using ZC winds up not introducing a particularly huge amount of error, even in the worst case scenario. So I think we saw that it got up to in the ballpark of 4-ish%, okay, for some frequencies.
Why did not you?
So that's a very good question. We're about to, like, the Z is effectively buried inside of this. So this is the results of after doing the manipulation that I'm about to do. Okay? So like I said, I've jumped forward a few steps to see what the impact of replacing this ZC with this RC is in our frequency response. James, I think you had your hand up.
No,
Okay. Okay. So let's play around with that bit there and we'll see what happens to the ZE. Okay, so I'm just looking at this bit I have here on the right. Okay, so I have 1 divided by. So let's put the ZE in now. Okay, so ZE times 1 plus GM R naught divided by R naught plus RC plus ZE over R pi plus 1. So I have a common factor of ZE in those first 2 terms. So I'm just gonna, yes.
Should you have a?
I'm only messing around with just that part to see what shakes out. Okay, so this is just, so I don't have to keep writing down that negative GM R naught in parallel with RC thing over and over and over again. Because that's an isolated thing as far as I'm concerned. Okay. So we know that ZE is RE divided by 1 plus S RE CE. And now over here, I'm going to have 1 plus GM R naught divided by R naught plus RC plus 1 over R pi plus 1 as my denominator, and just 1 in my numerator. We okay with that? So what I'm going to do now, because I don't like having fractions and fractions, is I'm just going to multiply through by 1 plus S R E C E on the numerator and the denominator. And so what that's going to give me is 1 plus S R E C E in my numerator divided by RE times 1 plus GM R naught over R naught plus RC plus 1 over R pi plus 1 plus S RE CE, which is what was in my MathCAD sheet. I just skipped a couple of the steps ahead just to make sure the error worked out okay by making that assumption. So are we okay with the algebra involved getting to here? Anybody see anything jumping out at you that I've made a mistake on? If so, we may derail this lecture until Monday, but it'll be okay. I feel like I did it correctly. Everything look legit? Okay. So what I have here is something that I can easily extract a 0 from in the numerator and something that I can easily extract a whole from in the denominator, right? So we could say that we'll have, I'm going to call this omega z amp 1. So this is just our first 0 from our amplifier analysis. And that is just -1 over RECE. Just coming from what's going on in our numerator. And then we'll have omega P amp1. And that's going to be negative RE times 1 plus GM R naught divided by R naught plus RC plus 1 over R pi plus 1. That whole large resistance there divided by REC. And to be clear here, all I've done is I've just taken everything that isn't in the S times something and divide it by whatever's being multiplied by S. And then I throw a negative sign in front because our poles need to be negative for our system to have stability. And it's from the positive sign. So we've identified the first pole and zero of our overall system's transfer function. We've made one extremely small assumption, introducing well under 1% of error, and then one assumption that is introduced between, I think it was like a tenth of a percent up to 4% error, depending on what frequency we're looking at, okay? So we're in relatively good shape here. So we figured out this part right here contributed a pole and a zero. And so now we're going to look at this part right here. Let me throw boxes around these for while we're at it. All right, so negative GM R naught in parallel with ZC would be negative GM R naught times ZC over R naught plus ZC. We're all okay with that, I hope. I'm just going to move this down just a smidge to give myself a little bit of room. So I'm going to pull the negative GM R naught out of this bit. So now I have ZC in my numerator, which is just RC times 1 plus S RLC out over 1 plus S RC plus RL C out divided by R naught plus that same thing. We all okay with this? So what I'm going to do next is I'm just going to multiply by this denominator here over that same thing to effectively clear out those denominators. Okay. And so what that's going to do let's take that over here. So I'm gonna have negative GM R naught. I'm pulling the RC out of the numerator of the numerator. Fun times are ahead, obviously. And then I'm going to have one plus S RL C out up here, divided by R naught plus S R naught RC plus RL times C out plus RC times 1 plus, actually, let me do this one thing further here. I am going to move this RC right here inside of this parentheses. So that's going to be RC plus S RC RL C out. Yes, so let's look at this and see if, make sure I didn't screw anything up or explain what I need to. Hannah, what do you got?
It's all
I'm sorry, what was that?
to the R.
So let me walk you through what I did here, okay? So first step, I took this R naught and I pulled it out over here, which is where I get this negative GM R naught from. Then I simply substituted in ZC over R naught plus ZC. Are we okay with that? Okay. Then, let me erase this bit here. I took this RC and pulled it over here, which is what gives me this. What I did next, and I'll do it out here in blue, is I just multiplied by 1 plus S times RC plus RL times C out, divided by 1 plus S times RC plus RL times C out. So what that winds up doing is this part right here cancels this part right here. This part right here cancels this part right here, but I have to remember to multiply it by that R naught. So that's what this part down here represents, where the R naught is distributed inside of that thing. So instead of having R naught times 1 plus blah, 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 I have R naught plus S R naught times the same junk. So did I make an algebraic mistake? Oh, it's an RL, sorry. You literally just couldn't read my handwriting, you couldn't follow my math. I feel like such a jerk. Sorry, that is an RL. To be clear here, it's coming from this bit right here, which is, I hope, very definitively looking like an RL. Yes, sorry about that for mansplaining math to you when you literally just couldn't read my damn handwriting. I sincerely apologize for being more of a jerk than usual. All right. Thank goodness we recorded that. Okay, so I can lump things together now a little bit here. So negative GM R naught RC. My numerator is going to stay the same, 1 plus S R L, C out. And I'm going to lump my R naught plus RC together. And then I'm going to lump all of my S terms together. So that's going to look like R naught times RC plus RL plus RC times RL times C out. We okay with that? And now I'm just gonna divide through by R naught plus RC to get my mid-band gain back out of this thing. Okay. So that's gonna give me negative GM R naught in parallel with RC times 1 plus S RL C out in the numerator. And then 1 plus S times R naught times RC plus RL plus RC times RL, all divided by R naught plus RC times C out. And once again, I have things in a form where I can easily identify both a 0 from the numerator's polynomial and a pole from the denominator's polynomial. So we can say that omega z amp 2 is just negative 1 over RL C out. And omega p amp 2 is going to be negative 1 over R naught times RC plus RL plus RC times RL divided by R naught plus RC times C out. So we have finished our analysis of the amplifier stage. The analysis of the output stage is really simple. We've got 3 minutes left of class, and I legitimately think I can do it in those 3 minutes. Okay. So let's look at the output stage really quickly. So here's our voltage Vy. And between the collector node of our transistor and ground, we see the resistance RC, the capacitance 1 over SC out, the resistance RL, and our output voltage is just the voltage drop across this resistor, RL. So I want to be clear here. The resistance RC is effectively in parallel with that voltage Vy. So it's not going to show up in our voltage divider equation because the voltage doesn't divide over it in any way, shape, or form. So instead, all we have is V out over Vy is R over L, excuse me, RL times 1 over SC out plus RL multiplying through by SC out over SC out gives us SRL C out divided by 1 plus SRL C out. And so the 0 associated with our output node is 0. And the pole associated with our output node or output stage is -1 over RL C out. And this is where we'll be stopping for today. So all we've got left to sort out is the input stage. And this is one of the things where I did a ton of algebra and I'm skipping 99% of it for you guys. Sure.
Yeah, right. Are we gonna do like this process for each type of amplifier?
Yes. Yeah. For what it's worth, this is by far the hardest. Yes, Matthew.
This is kind of related, but not really. So if you have an active filter, or would active filters behave better at lower frequencies compared to like an inactive filter in general?
The purpose of an active filter is to provide gain while filtering. So the filtering characteristics are dependent on what the components that you're putting in there. The active part is just you're using an amplifier as part of that.
I should know like more consistent. I made it out. What is? That's a pole. President. Right here.
So you might want to go back to your circuit 3 notes. So whenever we have a 0, we expect to see a 20 decibel per decade increase in our transfer function. Whenever we see a pole, we expect to see a 20 decibel per decade decrease in our transfer function. Yep. So like if we looked at this LT Spice thing right here, right? So I'm looking at what's going on right here at 200 millihertz. Where the magnitude of our transfer function is -10 dB. Well, if I look at 20 millihertz, which is 1 decade away, now it's -50 dB. So the difference in there is 40 dB. So we have increased 40 decibels in 1 decade, which tells me somewhere below that frequency, there was 2 zeros. So we are increasing at 40 decibels per decade. And then somewhere, and I say somewhere, exactly at this frequency, whatever it is, we must have hit a pole because now it starts to taper down to just 20 decibels per decade. Yes. And then when we get to here, we had to have hit another pole to make it completely flatten out. Yep. Yep. And then over on this side, we're flat, and then we hit a pole, and then we hit 2 more poles to make it decay even faster. And then it looks like we hit a whole bunch of zeros over here to make it completely flat now.
Pole to 0, which is basically the value that we get along and that'll change with rate of change.
Exactly right. Yep. Exactly at the pole, you should see a 45-degree change in the phase. which is why, so like right here, we're at 0, and then when we cross right, ooh, crap, well, I just lost it, but anyway.
Yeah, you can zoom it.
So this is negative 45 degrees, which means we just hit a pole.
Yeah.
Where do you see it's negative?
Over here on the right.
Oh,
Yeah.
Yeah, so looking at the phase, the dashed lines,
Okay. yeah.
because we hit negative 45 degrees right around here, this means we've got to have a pole right around here. Right, and down here where it's hitting negative 90 means, well, we had another pole. Or actually, no. So this is telling us exactly where, but the transition from 0 to 90 means that we're passing through the pole. So, right, so it should start transitioning at about 1/10 of the pole frequency, and it should stop transitioning at about 10 times the pole frequency. So now we're settled here at negative 90, and then we obviously hit another pole somewhere in the ballpark here. So wherever it's negative 135, that's the location of another pole. Yeah. So, yeah, we can glean a lot off of the frequency response. Mhm.